Thank you. Good morning, everyone. Today we have the 19th lecture in the Cloud Physics lecture series by IITM. And today's lecture is given by Professor Kirti Sahu. He's from Department of Chemical Engineering, Indian Institute of Technology, Hyderabad. So he will be talking about the microphysics of droplets in an airstream. I request Dr. Mahen Konwar to introduce the speaker. Thank you.
Yeah, thank you, madam. Yeah, this is a great pleasure to invite Dr. Kirti Sahu and to introduce Professor Sahu to this talk. He is a professor at the Department of Chemical Engineering, IIT Hyderabad, and he obtained his PhD degree from JNCSR Bangalore in 2007 and was a postdoctoral fellow at the Imperial College London from 2006 to 2009. And then he joined IIT Hyderabad as a faculty. His research interest includes the study of clouds and raindrops, interfacial flows, and hydrodynamic instabilities. Professor Kirti has received many recognitions. For example, Young Scientist Award from the Indian National Science Academy, National Academy of Sciences, India, Young Associate of Indian Academy of Sciences, and VASVIK Award. He is an elected fellow of the Institute of Physics, UK, and he served as an associate editor of the Journal of Engineering Mathematics and Fluid Dynamics and Materials Processing. Yeah, with this introduction, we invite him to the talk today. Hello.
Yes. Yeah. Shall I start?
Yeah.
So thank you very much for your kind attentions and inviting me for giving this opportunity to speak here. Am I audible or I should be louder?
Yes, yeah. You are audible.
Yeah. I'm Kirti Sahu from IIT Hyderabad. Today I will talk about microphysics of droplets in an airstreams. So this is the outline of my talk. We'll start with some general discussions on bubbles and droplets. Then we'll talk about dynamic of a freely falling droplet. And then we'll move on to discuss about interactions of droplet with an airstream. In this case, we'll have a horizontal airstreams interacting with a droplet. And then we'll discuss about interactions of droplet with a swirl airflow, which actually we can frequently observe in atmosphere. Then finally, we'll talk about size distribution of satellite droplets after it fragment out due to the air current using inline holography technique. This is one recent techniques which has been being popular to study droplets dynamics. So to start with, droplets and bubbles can be found everywhere, starting from, let's say, chemical engineering applications like fluidized bed, inkjet printing. To this audience, I need not have to say that the shape and size of the droplets plays very important role in weather forecasting and rainfall modeling. This pictures at the bottom, you see the mode of volcanoes bubbles. So what happened is the methane bubbles, which are stored in the lake or somewhere, it comes out as a bubble and it forms these craters, and then it bursts to form these holes. So measuring this crater size and the holes essentially can, using that, we can estimate the intensity of volcano. This picture shows a dolphin moving that forms a toroidal bubble at its wakes, and that helps it to take a turn. This is a fascinating example, as you can see, of a droplet falling on a liquid pool. So to our naked eye, when the droplet falls on a liquid pool, we all think that it will just go and submerge inside the liquid. But it never happened like this. If you put a droplet slowly on the surface of a pool, it creates an air cushion between the droplets and the free surface of the pool. And it keeps floating till that air cushions drain out. And then finally it coalesces to form a satellite bubble. mostly the volume of the satellite bubble is half of the previous bubble, and this cascading process continues till the entire droplet submerge inside the liquid pool. This we know that droplets on different surfaces have motivated many microfluidics applications. So we can say that bubbles and drops are not only relevant in many engineering disciplines, but also interesting. This is in the context of current situation, studying the droplet coalescence, and there is some noise coming. Is it from my side?
There is no noise.
Okay.
Yeah.
Studying the droplets, the coalescence, and the distance travel when a infected person coughs, sneezes, or let's say talks, understanding that thing can give us an idea of using face mask and how much social distancing one can maintain in the context of COVID-19. When a infected person talks, droplet goes and maybe stays on some surface. Studying the lifetime of these droplets also tells us how much time the surface will remains infected. So because of this, many fluid dynamics people have come forward, particularly the droplets researchers, and investigated this problem and came up with many helpful findings. This is an example of our Indian pictures of our Indian monsoon. To this audience, at least, I need not have to say anything on this, but I'll just briefly say what happened is air containing a lot of water vapors from southern hemispheres actually migrates towards these triangular regions between India, Pakistan, and South Africa. When it reached to this place, something different happens because of the geography, and air take a turn and enters to our country, and that is the starting of our monsoon seasons. And then what happens is it migrates and then hits Himalaya and come back. So if we relate monsoon to the rainfall, it's similar everywhere, but Indian monsoon is truly unique because it's an enormous movement of water and energy across earth, and the number of variables which actually affect the Indian rainfalls are really huge. Last year, Professor Carl Sossalman, who is a Nobel laureate in physics last year, illustrated how rainfall modeling adds to the understanding of global climate change. And now, because the Indian monsoon is complex and a very unique phenomena, understanding that rainfall will be definitely much more helpful to understand the global climate change. These are some of the grand challenges in environmental fluid mechanics, and you can see that the clouds and studying of raindrops are very much part of these challenges. Now coming to the rainfall modeling, using raindrop size distribution, weather radar determines the type of rain, light, heavy, or big storm, and how long it will last, magnitude of rain, and location of rain. Essentially, it uses a formula known as Marshall and Palmer formula, which relates the average size of the droplets with the rainfall. So that's the reason it is, and understanding the shape and size of the raindrops are important. This is in satellite data I have taken from NASA website to show the size distribution of droplets during storm. The red region here indicates bigger size droplets, and the blue regions are the smaller droplets. Now, in order to understand the rainfall, we need to understand the shape and size of the shape size distribution of the raindrops, which is largely affected by the microphysics. For example, coalescence, breakups, and phase change. All these phenomena actually affect the size distribution of raindrops. For example, neglecting coalescence and breakups can, if we only neglect coalescence and breakup, it can introduce 10 to 20% of error in rainfall modeling. Then of course, when we neglect evaporation, airstream, etc., the error can only increase. Bigger raindrops are non-spherical. For example, if we have some tiny droplets of 1 millimeters, due to surface tension effect, it will be spherical in shape. But as we increase the size of the drops, it will become non-spherical. This is a very simple shape I have drawn here, but it can be even much more complex than what we see for a 7 millimeter droplet. Now, because they are non-spherical now, it will introduce significant error in calculating the average diameters, and thereby the rainfall predictions will be erroneous. So these are some of the current state-of-the-art experimental facilities available to study clouds and raindrops. This one was developed by Professor Rodam Narasimha at JNCSR. This is a cloud chamber. This is in Manchester. This is known as ice cloud chamber, and the height of this is something like around 10 meters. This is the tallest one at present, they say. There is a group in Germany who have set up these cloud chambers at the top of this mountain, and this is the tallest mountain of Germany. In 70s, Prupachers and co-worker, they have used a cloud chamber known as UCLA cloud tunnels, which was actually around 35 meters long, but now this facility is no longer available. The cloud chamber, a cloud chamber was also developed by Professor Jayavant Arikari at IISc Bangalore. Now, if you come to the raindrop side, the number of facilities are very less. Because, for example, when a raindrop, let's say, fall from the sky, the humidity is supersaturated and the temperature is below 0 degrees centigrade. As it falls, the humidity increases, humidity decreases and temperature increases. So in order to study the raindrops, one has to build a tunnel which is, let's say, 2 kilometer height, but that is not possible. This Menged people, Menged vertical wind tunnel, Germany, they have come up with an idea that they will keep the droplet stationary by moving the air from the bottom. But they have not considered the evaporation and other complex, the microphysics of raindrops. Only they studied the shape oscillation of droplets. There is an experimental facility at IITM Pune by Dr. A.K. Kamra groups. They have a cloud raindrop facility, and using that they studied the effect of electric field on raindrop dynamics. I have been talking with Dr. Tara Prabhakaran and requesting her to show me, and they have the rainfall measurement using weather radar. So getting some data from them will be interesting to compare with our experimental studies. These are some of the encouraging articles. All these articles was given to me by Professor Rodam Narasimha. This article, all are from, of course, Nature. This article says that the physicists, your planets need you. This article highlights the fact that building high resolution global climate models are very essential. The third article actually talks about the dynamics of small and large raindrops. Even simple questions is difficult to answer as far as the raindrops are concerned. For example, do all raindrops fall at a terminal speed? If we have a solid object, let's say falling under the action of gravity, we can easily calculate the terminal velocity by balancing the forces. Let's say gravity is acting in this direction. So the mass into acceleration acts in the downward directions. Weight of the object acts in the downward directions. The drag force and the buoyancy force acts in the upward direction. So if we balance it and set this acceleration to 0, you will get the terminal velocity. But droplets are not like that. It has a lot of complex phenomena, interfacial phenomena due to surface tension, and also which actually acts right at the interface. And also it will have the density contrast between the inner and the outer surrounding medium, and the viscosity contrast, which will affect the interfacial stress balance at the interface between separating these two fluids. So simple questions like I mean the answer of this is do all raindrop falls at terminal speed? The answer is actually no. So many and that is due to the fragmentations, coalescence phenomena, phase change phenomena occurring while as the raindrop fall from the sky. Now, in order to study a falling raindrops, if one has to do a numerical simulation, the governing equations are continuity equations and the Navier-Stokes equation. In the Navier-Stokes equation, this term is essentially the inertial term. This is a pressure gradient. This is viscous terms. These two terms are associated with the surface tension, and the last term is essentially due to the body force. Now, this term will only come into picture when one has the interfacial gradient along the interface. This is essentially the normal component of the surface tension force, which will be there all the time. So in order to study a raindrop, one has to consider a very big computational domain because otherwise there will be the boundary effects which will affect the dynamics. Let's say if we have a droplet designated by fluid B falling in air designated by fluid A, and if we do a Buckingham-Pi theorems, we can show that there are 4 dimensionless numbers needed to describe this problem. First one is Galileo number. This is actually the gravity force by viscous force. This is similar to Reynolds number, but Reynolds number is defined generally based on the terminal speed. And in the last slide, we have discussed that raindrop all the raindrop do not falls at the terminal speed. So it will be, I mean, erroneous to define Reynolds number using the terminal velocity. So the most appropriate number is the Galileo numbers. Then we have Yotto's number, which is gravity force by surface tension force. This is similar to Bond number. Density ratio, density of fluid B by density of fluid A, and viscosity ratio, viscosity of fluid B by viscosity of fluid A. So for an air water systems, for a droplet falling in air, mu r, the viscosity ratio will be 10 to the power 2 and density ratio will be 10 to the power 3. Now if it is a bubble falling in water, it will be opposite. It will be 10 to the power minus 2 and 10 to the power minus 3. Now I made this point and I'll try to show something on the bubble because I wanted to relate the bubble dynamics with the droplet dynamics. We all see in the aquariums when the bubble rises up in the fish aquariums, you see that bubble undergoes this wobbling motions. So this is from the numerical simulation for a typical Galileo number and Yotto's number, and you can see that the bubble rises up in a straight path for some time, and then it started this it turns this trajectory and goes through this zigzagging motions. So this is a zoom view of this bubble, and you can see that as soon as the bubble starts this oscillatory motions, it also goes through this asymmetrical shape deformation. The trajectory of this bubble is shown here. So when the bubble was rising in a straight path, just early time, when we plot the z component of the vorticity, the vertical component, they are mostly aligned. But as soon as you start this wobbling motions at the onset, you can see that the vortex shading occurs. So essentially now it is well known that the vortex shading and asymmetrical shape deformation is the main cause behind this wobbling motion. So I am saying this thing just to correlate the dynamics with the droplets. Now the question comes here which we ask is, can we observe oscillatory motion in the case of a falling liquid drop in air, like in the case of bubble, by changing the initial shapes to a non-spherical one, because the non-spherical bubble only can oscillate like that. So what is the effect of inertia on the droplet dynamics? and what is the role of vortex shedding, which is the main cause behind the wobbling motion in the case of bubble. So in order to answer these questions, we have considered two shaped droplets. One is oblate, wherein the horizontal diameter is bigger than the vertical diameters, and the prolate shaped droplets, wherein the horizontal diameter is smaller than the vertical one. And this is from our numerical simulations. We have plotted A minus B, the horizontal diameter minus the vertical diameters, with time. And when it is A minus B is 0, essentially it is a spherical drops. And this has been done for different aspect ratio, initial aspect ratio of the drops. And you can see that when the droplet starts with a spherical shapes, when A by B is 1, it remains spherical. You can see that the line is almost going through this 0. But when it starts from a non-spherical shapes, like a oblate, prolate, or any tilted shapes, it continues to oscillate for very long time. Another thing you can observe here is the amplitude of oscillation decreases slightly. Okay, so in order to understand this, in Inviscid theory we have conducted following the Lamb formulations, and this is essentially the frequency of these oscillations, and for a fundamental mode n can be substituted to 2, and this alpha n represents the decay rate. As I told you in the previous slide, there is a decay in those oscillations. So here we have plotted the time period, which is 2 pi by omega n versus Yotov's number for a typical parameters for a droplet, which is Galilean number 100. And you can see these are from the numerical simulation, the dots, and this line represents from the theory, and you can see that they are matching very well. Now for a typical raindrops, let's say Galilean number 100 and Yotov's number 10 to the power minus 3, you can see here we have plotted this decay rate versus Galilean number for Yotov's number 10 to the power minus 3, and you can see that as you increase the Galilean number, the shape oscillations decreases, and when it reaches 100, it's almost negligible. This indicates that if a raindrops fall from a non-spherical shape, it will continue to oscillate till it hits the ground. Now these oscillations has a huge consequence. So for example, if we have two droplets, spherical droplet falling, okay, and even if they are in touch, there is for them to coalesce. I mean, it is difficult for them to coalesce. But if they are oscillating like this, and if they come closer, and when they are oscillating, they can hit each other and they coalesce, and thereby they can increase the size. Thereby the raindrop size will increase. So in fact, that is for using Inviscid theory. When we do a full 3D simulations, in fact the oscillation amplifies for Galilean number 100 rather than decreasing. It actually amplifies, and these are the shape of the droplets for these red points, and these are the shape of the droplet for these blue points. And you can see that at later time for Galilean number 100, you see some sort of nonlinear effects in the shapes. The shape is becoming much more complex than a oblate or a prolate shapes. So when we plot the vortex setting in this case, which was the root cause behind this wobbling motion in the case of bubble, you remember, here for Galilean number, you don't see any vortex setting. But for Galilean number 100, which is a typical parameter for raindrops, you can see a huge amount of vortex setting. But this vortex setting is now creating this nonlinear effects, and thereby making the raindrop shape much more complex. But the raindrops in this case still move in the vertical path only. It does not go through these wobbling motions. I mean the oscillatory motions. So in this case, the role of vortex setting is different from that of the bubble. So another question which we ask is, can a raindrop be hollow? The first mention of this idea goes back to the late 1800 by E.J. Lloyd. What happened is when the raindrop falls, it flattens out because of the aerodynamic interactions with the aerodynamics air currents. And at some point, due to the drift, it actually bends like this, like an inverted cup. And under some conditions, they can close from the bottom and forms a hollow drops. Another way it can form is when this ice crystals, in the cloud, we have this ice crystal surrounded by liquid. Due to heat of condensation of the vapor, this ice phase will directly go to the gaseous phase without going to the liquid phase. So in that case also one can observe hollow droplets. The dynamics of hollow droplet is much more complex than a normal droplet because it will have two interfaces. Here all these are from numerical simulations. You can see the inner one is an air phase, outer is air, and then there is a liquid phase in the annular regions. Here we have plotted the inner diameters of this inner bubbles and the outer bubble, and you can see that they undergo these oscillations. But the oscillation is much more complex because although we start with a concentric spheres, you can see that at later times the inner one becomes oblate, whereas the outer one is prolate. That means they go out of phase. Another thing which you observe is due to the gravity effect, the liquid from the top migrates towards the bottom side, and thereby increasing the thickness of the liquid phase at the bottom side. And due to the Rayleigh plateau instability, you can see that the air, the liquid actually dripping from the bottom. So it undergoes a different type of breakup modes when we have a hollow drops. So what we have discussed so far is we discussed about the dynamics of a droplet as it is freely falling in air. Now we'll discuss what happens when the droplet interacts with an airstream. There are three different configurations possible in this case. One is cross flow. The droplet is falling vertically, and then the airstream is moving like this. It is a cross flow configurations. Then we can have opposite flow configurations wherein the droplet falling in the vertical direction and the airstream is moving in the upward directions. And co-flow configurations wherein we have both the droplet and the airstream moving in the vertical directions, in the same directions, and they can interact. So we have three configurations: cross flow, opposite flow, and co-flow configurations. This is from our experiments. Here we have a droplet falling, and this is a nozzle wherein we create this airstream, and that breaks the bubble droplets into satellite drops. For this, we have a dispensing needle to create the droplet, and then we have this nozzle which will create a uniform airstream, and then we have high-speed imaging systems with backlights and so on to record the video. So we can see that as the droplet falling, it interacts with the airstream. It forms a bag, and it ruptures. The bag ruptures from the front, and then what you see is the film, the remaining film, attracted towards the rim, and then the rim also fragments out to entirely breaks into tiny droplets. So this is of course at an angle incline. The nozzle is at an incline, creating the airstream at an inclination. The breakup process is detected by the inertia force. acting on the droplets. So the most relevant time scale, which is in this case is of the order of millisecond, can be defined like this. So when we have this horizontal airstream, we have a dimensionless number known as Weber number, which is inertia force by surface tension force, will define different breakup modes. So here we show the droplet shapes at different time instants for different Weber numbers. For low Weber number, let's say Weber number 7.87 in this case, the droplet undergoes the shape oscillations as it interacts with the airstream. Now, as we increase the Weber number to, let's say, 8.27, this shape oscillations becomes significant, and the droplets will break to form the satellite droplets of relatively larger comparable size. As we increase the Weber number further, you can see that the droplet form a disc shape like this, and then due to the relative instability, there is a airstream pushing it. So we'll discuss about the relative instability later. But we can see that it forms a bag, and now the bag, the size of the bag increases, and then there is a rupture at the tip of the break, and then you can see that this film will get attracted towards the rim, which is here, and then subsequently this rim also will break to form satellite droplets of very small size. This is, of course, for an airstream which is in a cross flow configuration. The droplet is falling like this, and then there is a airstream which is hitting the drop like this. Now, if the airstream is at an angle, now it is interacting with the droplet at a certain angle. You can see this is called oblique airstream. You can see we get this vibrational mode for Weber number 5.13. This was 7.87 in the previous slide when it was horizontal. Similarly, we got this transitional mode at Weber number 5.73, which is much lesser than that which you observe in the horizontal airstream. Even the bag breakup mode occurs at a much lower Weber numbers as compared to the horizontal airstream. So what we can conclude from here is the critical Weber number requirement for the bag breakups decreases as we have a airstream interacting with a droplet at a certain angle. So even the trajectories are different. This has here we plotted the trajectories of this vibrational mode, transitional mode, and bag breakup mode, and the predicted one also. So you can see that when we have this horizontal stream alpha equal to 0, a pure cross flow configurations, the trajectory of the droplets are like this. But when we have an angle 30 degree or 60 degree, the droplet comes like that, and now it interacts at an angle, so it take a turn and goes in the upward direction. So here we see the effect of droplet size on the bag breakup phenomena. So as we increase the droplets size, the critical Weber number at which the bag fragmentation occurs actually decreases, and also this time shows the maximum size of the bag before it ruptures, and that has been done for alpha equal to 0 pure cross flow configurations, alpha equal to 30 degree, and alpha equal to 60 degree. So what we can observe in this from these results are summarized here. So as we increase the diameter of the drops, the time at which the back breakups occurs increases. You can see Yotov's numbers and Weber numbers are defined like this. As we increase the diameter of the drop, both Yotov's and Weber number increases, but Yotov's number goes in d square and Weber number goes in as d. So what happens is Yotov's number increases faster at a faster rate as we increase the d. So what happens is Yotov's number essentially tells that the gravity force by surface tension force. Now as we increase d, the Yotov's increases faster, thereby decreasing the surface tension effect, and hence as we increase d, the critical Weber number requirements for back breakups decreases. This is to summarize the results as what we have discussed earlier. Here we have critical Weber numbers versus alpha. Alpha equal to 0 essentially is the cross flow, and alpha equal to 90 is opposite flow. And Bellurmarx and Bosa they showed that the critical Weber number for opposite flow conditions is 6, and for cross flow it is around 12. Here you can see that as we increase the Yotov's number, the critical Weber numbers decreases for a fixed configurations. Moreover, as we increase alpha for a fixed Yotov's number, you can see that for let's say Yotov's number 1.1, the critical Weber numbers decreases from all the way from 12 towards 6, and about 60-degree inclinations you reach actually as the value of 6. So this is from our study where we capture the critical Weber number requirement from all the way from cross flow to opposite flow configurations, and this is to the best of our knowledge for the first time we have shown this. These are earlier studies which actually shows the critical Weber number for different configurations. And most of the studies were done in the cross flow configurations, and they showed that the critical Weber number requirements is about 12. In the opposite flow, as I discussed, Bellurmarx and Bosa showed that it is 6, and we have recently shown that the critical Weber numbers goes from all the way from 12 to 6 as we increase the inclinations of the airstreams. Now, what we have discussed in the previous one is when the droplet interacts with an airstream in the opposite flow configurations or in the co-flow configuration, but the airflow is straight. What happened to the dynamics? Now, in many situations in the atmosphere, we observe swell flow. We observe this swelling type of flow. So for that, in addition to these Weber numbers, we will have a swell number. This has been defined based on the geometry of the sweller. Di represents the inner diameters of the sweller, and D naught represents the outer diameters. So for a fixed sweller, the swell number is constant. Of course, a droplet, when it interacts with the swell airstream, it will encounter cross flow, co-flow, and opposite flow conditions simultaneously. So the location of the dispensing needle, or at which the droplet starts interacting with the flow, also becomes important. This is an experimental setup. Now, because the droplet can undergo the 3D motions here, we have used 2 cameras, and this is a nozzle with a sweller, and these are the light source to helps to capture the images. This is for a this result shows for a fixed Weber numbers 11.40, and the results shown are shown for different swell numbers. For swell number 0, for these parameters, you can see that the droplet undergoes these vibrational breakup modes, the droplet first forms a disk shape, and then the oscillations amplifies, and then it fragments into droplets of comparable size of larger droplets. In the when we increase the swell number, when we put a swell number of 0.47, we observe a new breakup mode. Here, what happened is the droplet forms a asymmetrical shapes, as you can see at time t equal to 4.16. What happened is the bottom part of this droplet encounters a opposite flow, whereas the top part encounters a co-flow configuration. So what happened is the liquid from the top migrates downward, thereby increasing the thickness of the bottom part of this droplet. So what happened is, in this case, only the top part will participate in the bag formation process, whereas the bottom part is still become thicker, and and because of the swell, it will undergo some sort of twisting type of dynamics, wherein the top part will go forward, whereas the bottom part will retract back in the upstream directions. So and then because of this twist, the droplet will fragment into satellite droplets. Now this is a pure breakup. When we put the swell number, put a very high swell number, so what happens is the droplet the aerodynamic force is so sufficient that the entire droplet participates in the breakup process, and you can see that the fragmentations into tiny droplets occurs in this case. So this is the movie of the previous one. The first one is the vibrational mode. The middle one is the retracting back breakups, and the bottom one is back breakups for high swell case. And you can see that this is a new mode which you observe, the middle one, and you can see that the droplet undergoes this retracting phenomena. The top part is going in the forward direction, whereas the bottom part is retracted back, and the droplet undergoes this twist, and then it fragments. This is essentially two view, front view and the top views of the same droplet. Whereas in the case of back breakups, you can see that the droplet fragments into tiny droplets. First the back fragments, then the film attracted towards the rim, and then eventually the rim also fragments out to form satellite droplets. Of course, we have done then a lot of experiments to come up with the regime map, which shows different breakup modes for let's say swell number 0.82. I'll not go into detail of this, but I mean, these are the summary of a lot of experiments which we have performed to show different breakup modes. The circles ones are the vibrational modes, triangles one are the retracting back breakups, and the stars are full back breakup modes. We have also done by varying the location of the dispensing needles. I'll not go into detail of this, but we have come up with some regime map, and one can say by varying the swell number how under which region we'll get the retracting back breakup or back breakup phenomena. This is in order to study the flow, we have also conducted Stereo-PIV experiments, and this is for swell number 0, the first one. Here we have plotted these contours of the resultant velocity ux square plus ua square plus uz square, and you can see that there is a clear potential flow core regions indicated by this red region, where the droplet interacts with the airstreams of this red part and fragments out. In the swell flow, you can see clearly a coronal type of flow. The bottom part, the center part, essentially the velocity is low because of the dome shapes. So the airflow is minimum there, but most of the airflow is occurring in the annular regions, and that you can see a coronaryl type of flow here. The velocity maximum occurs at the top in the annular regions essentially. So as we increase the swell strength, you can see that a lot of mixing occurs and flow becomes more or less uniform type. And that's the reason it undergoes the full breakup phenomena when we have high swell numbers. Now, what we see here is as a droplet falling, and then there is a airstream going now and hitting it. So essentially, a lighter fluid is now displacing a heavy fluid. So and thereby creating the relateral instability. So what happened here is, as the time progresses, the spherical drops of diameter d naught will flatten out this is the radius RT and the thickness HT, and then it undergoes through this bulging effect of forming the bag with its length L, which is a function of time. So this H is a function of time, R is also a function of time, and L is also a function of time. Now, as the time progresses, this rim will form these nodes, as you can see here, the finger-like structures. Now, this has been done using two views in our case, front view using two cameras essentially, front view and top view. And you can see that in the front view, only 6 fingers are visible clearly, whereas in the top view, 3 more fingers we can clearly see. Now, this number of fingers will be used to understand this relateral instability. So, the counting the number of fingers are very much important. So, here we have plotted the number of fingers versus Weber numbers. The earlier studies are shown by the stars here, and you can see that they predicted even for, and their case is swell number 0 case, of course. Our swell number 0 case predict the number of fingers higher than what they have observed. That is because we have used two views, whereas the earlier studies use only one view, so they missed these three nodes in this particular example. Of course, when we increase the swell number, the number of fingers increases. So and thereby it decreases the wavelength of the critical modes. So if the number of fingers increases, the wavelength between these nodes will decrease, and swell flow essentially and thus the swell flow essentially enhance the stretching factor, because increasing the swell will increase the number of fingers. So with some little bit of mathematics, one can get an expression for alpha, which is defined as R, how this R radius increases with time. Is a normal non-dimensional radius of this disc shape. So RT divided by d naught by 2. Similarly, one can get an expression for beta. Beta is essentially length of this bag, which will increase with time, normalize with the initial radius of the drops. And essentially the wavelength, knowing the number of fingers and knowing the diameters, essentially one can calculate the wavelength of the most unstable mode, which in this case is √3 to the lambda c. Lambda c is given by this, which is the critical wavelength of RT instabilities. Now, when we compare this theory which we have developed with our experimental results, interestingly, they match very well. Here we have plotted alpha t versus time, non-dimensional time, and beta t versus time, and you can these points with error bar essentially shows our experimental results, and this dashed line shows the results obtained from theory. And you can see that for swirl number 0, swirl number 47 and 48, all the results actually match very well with the theoretical predictions. Same thing happened for beta also. Now, so far what we have done, what we have discussed is either we have studied the shape oscillation of the drops or the fragmentation process. But that is not enough. As we discussed in the beginning, the raindrop size distributions is important. So we have to count the number of satellite drops, and that will go to the weather radar. So I mean, for example, if we have a droplet, and then let's say there is another droplet at the back, and if we are taking a pseudography, you are taking a picture, you will not be able to see the drop which is behind, right? So so thereby calculating the wrong numbers of droplet present in the after fragmentation. So holography is a new technique, a new paradigm which can be used. This is a machine learning type of machine learning technique which can be used to calculate the droplet shapes. So what it does is, I'll just briefly say something. So it will it has a laser and it will calculate the particle field and then image sensor, and then it creates a hologram. Now this is the holograms. Now varying the focal length, one can get the different slices of this image. So using the coherent lasers, one records the interference patterns by high-speed imaging, then reconstruct the volume to get the 3D shapes and position of the droplets, and then convolutions neural networks based machine learning technique to obtain the droplet size distribution. I'll show you the picture so that will be it will be clearer. So this is a demonstration in a straight flow, of course. So a droplet from this bag and then it fragments out, and from this fragment pseudography image, one can record a holograms which will look like this. And now if we increase, if we change the focal length, one can get the droplets. For example, if we take a slice at x by d naught at 0.9, just don't worry about this number, but it is a slice, and this is at different slice at different locations, and you can see that the droplet shapes, particularly in this region, you can see the droplet shapes are clearly visible here, whereas it is not that visible in this case. So one can not only get the droplet size distribution using the holography, inline holography technique, but also it can construct the 3D shapes of the drops. This is a demonstration of holography reconstruction, and you can see let's say a droplets here at different focal length. You can say that you can see you can actually not only calculate the droplets distributions, you can also construct the 3D shapes of these droplets. So this is a typical example of droplet distributions after fragmentation for Swirl number 0.82 and Weber number 12.69. You can see the first image is pseudography thing. The droplet fragments out from the bag, and then bag fragments out to satellite drops. This is the holography images, and from this image, using the CNN based machine learning technique, one can get the droplet size distributions. And N here represents the number of droplets, and D represents the average size of I mean the average size of the drops. And when we plot the, let's say, the average droplet size versus time, and let's say for Swirl number 0.47 and 0.48, we know that 0.82, the droplet fragments into tiny pieces as compared to 0.47. So you can see that the droplet size, average size of the droplets are lesser than 0.47, but it actually increases as the time progresses, because first the bag ruptures and then rim ruptures to form the tiny droplets at later time. So as the time progresses, the number of satellite drops increases. So essentially, this gives us the not only droplet size distribution, but also the 3D shapes of the satellite droplets, which may help in the rainfall modeling. This is a take-home message from this talk. This is the last slide, last but one slide, of course. I would say that physicists and engineers, your planets need you, because our planets is crucial, and understanding the rainfall will help us to understand the global climate change also. So finally, I'd like to acknowledge my students and collaborators. Pawan, Someshwar, and Surendra have done these experiments. And I collaborated with Dr. Pankaj Kole and Dr. Lakshmana Chandrala in this particular experiments. And I'll also like to thank SARB for financial support. Thank you very much for your kind attention.
Thank you, Kirti. Very fantastic talk. And Mahin, please see for questions from YouTube.
Yeah, thank you. There are a couple of questions. First question is from Dr. Raghavendra Asrit. He's asking, how are respiratory droplets observed and studied?
Oh, so when a person sneezes or coughs, right? So what is that? I mean, all the studies are done in mostly in numerical simulations. So you create a jet-type structures, and then it creates some droplets, and essentially you study how much these droplets will migrate. Because if the size of the droplets is more, it will migrate more. If the size of the droplets are small, it will migrate lesser distance. So for example, if somebody is talking and the droplets are created, so it will migrate less distance. But if somebody is sneezing or coughing, it will create bigger drops, and that will migrate longer distance.
Okay.
Yeah.
Are there more questions?
Yeah, I think his voice is not coming.
Mine?
Hello?
Yeah.
Yeah, I can hear.
Okay. Yeah, then there is another question from Dr. Praveen Punde. He's asking, with increasing diameter at 0 angle, the bubble size increases, while at 30 and 60 degrees, bubble size decreases. What causes this?
Oh, so I think he's asking about this case, right? So, so when it is a horizontal stream, what happened is when the droplet is, am I audible?
Yeah.
Yes.
So when the droplet interacts with the airstream in a horizontal streams, what happens is the droplets fragments in a very symmetrical way, and the critical, I mean the Weber number associated with this breakup are much higher than what you observe in an oblique airstream, particularly because of the instabilities. In all these cases, you see that the airstream, air which is a lighter fluid, is displacing a heavier fluid. So essentially, this is the development of Rayleigh-Taylor instability. So for example, if we have a lighter fluid at the top of a container, heavier fluid at the top of a container and the lighter fluid at the bottom of the container, the heavier fluid will penetrate down, forming this relatellar instability, and thereby, breaking the droplet fragmentations. So this is what is happening exactly in this case. So droplet is a liquid. Now it is interacting with the airstream. So air is lighter, droplet is a liquid, so heavier. So lighter fluid penetrating inside a heavier fluid. So when it is, interacting at a particular angle, so what is happening is we have a gravity force which is acting in the downward directions. We have this airstream aerodynamic force acting at an angle. So there is the competition between the gravity and aerodynamic force is causing the drops to break at a lower Weber numbers.
Okay.
Yeah.
Are there more questions?
Yeah, there are no more questions here. Yeah, our panelist, anybody has any question?
Anybody? I have a couple of questions.
Yeah, please.
Shivsai is there.
Yeah, hi Shivsai.
Hello.
Yeah.
Yeah.
Hi, how are you?
I am fine, thank you. Very, very nice talk actually, and excited to see very good experiments, because experiments are very rare these days, and very systematically done and documented experiments. I must say that I need to go through your papers very carefully to actually understand what you have said, but it was a fascinating talk, and I'm sure many of these are actually happening in the real world, and they are not isolated processes but occurring at the same time.
Correct.
So but of course it is very essential to even understand what is happening by doing systematic experiments. Excellent, very nice. I enjoyed the talk. Thank you. I don't have a question actually, but I just wanted to say this.
See, I only talk about fragmentation today. We have done some work on coalescence also, because when we say microphysics, it is actually not only fragmentation, coalescence, and also phase change. So we also did, we are doing something on phase change also. So this itself was almost 1 hour, so I cut that down. So, but we have done some nice experiments use for coalescence also.
Okay.
It will, I don't know. I mean, to this audience, I must ask a question. Again, this is a hypothesis and it is running in my head from long time. In our condition, coalescence is the main mechanism. It is somehow our droplets are coalescing more, and thereby the size of the drops is actually increasing. Is larger. So that is a hypothesis, but there is no. I'm thinking how to, prove it. So it is running in my head from several years. So
actually, I was also wanting to ask you on that collision coalescence. That part you did not touch upon in this talk at all.
Correct.
So, yeah, there is a very big scope to study that for large drops and maybe in comparison with observations.
Can I add something regarding this collision coalescence here? We have been doing some research on this drop size distribution using micro rain radar and also from satellite data and from ground-based observations like disdrometer. There we found that these drops actually they grow as they are falling down from the top to bottom.
Correct.
So we attributed this to collision coalescence.
Obviously,
but again, seeing your results, that they may be in the oblate shape also. Once it is in the oblate shape, if it is being dominated, oblate shape.
Yes, that's what also, I am saying. Yes.
Yeah, that also may give rise to higher radar reflectivity factor, or even say maybe equivalent larger drop mean diameter. So those aspects we have to see. Yeah, but as of now, we see that collision coalescence is a dominant process in our region.
In our region, correct.
And one important aspect is these observations we have are in very highly sheared environment.
Yes. Yes.
Yeah, so that indeed makes it more complex. See, you are indeed introducing a shear in your airstream. Also, there is a shear.
Correct.
And initially, that the asymmetric shape that you are seeing, maybe it is due to the shear, or
yes. So before it enters into the potential core region, it goes via a shear. You're right.
Yeah.
So regarding this coalescence, what I was saying is, let's say if we have two spherical drops to start with, it will fall spherically. So there is no reason for it to coalesce because they are falling vertically. They are not hitting like this. But now if we have these oscillations like this, if they come closer and they are hitting each other, they will just merge because there is an extra force. So that is essentially I came up with at least one mechanism that why our drops can be coalesce more.
Yeah. Madam, you have any question?
Yeah, I was just wondering whether Kirti, you looked at like multiple drops. Have you done any experiment with polydisperse drops? That is one question. And then regarding the have you attempted any way to estimate the breakup efficiency or the coalescence efficiency, because these are the parameters which may be needed in the models, and where we can directly connect with what is going on. So can you please comment on these points?
Yes. So currently, whatever the experiments we have considered was only 1 droplets and 2 droplets. This experimental facilities we are creating, it can handle this size is actually around 20 centimeters. So essentially, in one plane, I can put something like 20 droplets. So there I can, I mean, once this facility is developed, yesterday only we got vacuum pump. I mean, that is 3 tons. So it is really a big facility. So after this is done, then only I'll be able to do these experiments of multiple droplets at a particular altitude. So that's that part is still, I have to.
It may be something like you can do some experiments which are like in the real atmosphere, typical rain size distributions and typical atmospheric conditions, like that. Couple of experiments would really help to derive some useful parameters for the model.
That is the whole point, madam. So I will definitely go in that direction. But currently, we have developed the state of the art techniques. We have, I mean, frankly speaking, we have not gone to the raindrops. But now we are capable at least to study those dynamics.
Fantastic, really fantastic work, and we are very happy to hear you. And we look forward for your visit in IITM, and maybe we will hear more from you.
Yes, sure. I mean, I'm looking more than you. I'm actually looking forward to it from several years. I'm thinking, because COVID came and then everything stopped. So I hope you remember in Bangalore, I told that I'll come to you.
Definitely. I'm sorry that all these years we couldn't, but we will revive and.
Yes.
Before you conclude, I just have one question that maybe I didn't understand properly. So what exactly determines the shape of raindrop? Say it falls, we see sometimes it's totally spherical and sometimes prolapsed. But I think less oblate as I see. What exactly it is being determined by?
It's actually the shape of the drops will be essentially the competition between the inertia and surface tension. So now as the droplets is falling, it has an inertia. Now the surface tension will try to hold it to a spherical shape, whereas the gravity and the inertia will try to deform it. So if the inertia wins, it will become a non-spherical shape. And if the surface tension wins, then it will become a spherical shape. Essentially, if the size of the drops are very small, the curvature is more, and in those cases, surface tension will win. And hence the droplet will be spherical. But once it becomes slightly bigger size, there will be this inertia and the surface tension will become comparable, and they will form a non-spherical shapes.
Even it can keep changing the shapes, spherical to non-spherical. So what he explained, the surface tension and the gravity, they both are, it's a dynamics, like they can keep changing.
Yeah.
So, I interfere in between, but it really is very good talk, and I'm really very much interested in both the part. It's a, first thing is your phase change, which you have not talked. We can talk later on, and the coalescence, and also the shape, which I have worked long back during my PhD. I have worked this multi-phase flow using the volume of fluid method. And now I'm the cloud droplets only and phase change and everything. And the setup what Professor Arakari is doing. That is actually the project with, I'm the co-PI for that project. We are, we are doing the DNS for that setup. Still, we are not able to do the high Reynolds number experiment, but the numerical simulation has been done for that. So we are comparing that thing, but still going on. But I would like to see your this big facility, what you are talking about.
Professor Arikari knows about this facility. He talks with me a lot of many times actually. This facility will be mind blowing because I'm trying to create the atmospheric condition there. For example, it will start with 100% humidity and 0 degrees centigrade or less than 0 degrees centigrade. And as the time progresses, the condition, the air will decrease its humidity and increase its temperature. And thereby the droplet will experience the local atmospheric condition as if it is falling from the sky.
But are you going to create the turbulence, like you will have a relay alert type of setup?
So that's the reason we got this vacuum pump. We could have used the axial fan, but in axial fan you cannot control the turbulence. So whereas in vacuum pump you will have a much more, control.
So I don't see any questions in the chat box. I think all panelists discuss with Professor Sahu.
We will be inviting Kirti for further discussions physically. So I think there will be more interactions. And Kirti, we want to thank you immensely for accepting our invitation and giving this fantastic talk and enlightening us. Thank you.
Thank you very much.
Thank you.
Thank you.
Thank you.
Bye.
Thank you all. Thank you, everybody.